All right, so final chapter. This is chapter 28. So let's start talking about that. Time wise, I don't know how long it's going to take to go through this. It's probably going to be a little bit longer than an hour video, but it's something in that range. So there's about 37 slides that I want to go through, but a few of them will be a little faster paces. So it may be slightly longer in an hour, but I'm going to put all this in one video. So the topic of 28 is high performance liquid chromatography. So we talked about in 26 chromatography in general, 27 focused on gas chromatography. Chapter 28 focuses on liquid chromatography, in particular high performance liquid chromatography. So outline of things we're going to talk about: classification of LC liquid chromatography, when we need to use liquid chromatography versus gas chromatography. That's an important thing to understand. Talk a little bit about the instrumentation of HPLC, the pumps, the injectors, some of the detector options, and then we're going to talk about the four major phases of HPLC, which are partitioning chromatography, called reverse phase, absorption chromatography, called normal phase, ion exchange chromatography, and then size exclusion chromatography. And you can argue there's a fifth one called affinity chromatography today, but it's really a kind of a minority. I'll mention it just a little bit as we go through. And again, I'm not trying to overwhelm you with the problems, but I'm trying to give you an idea of some things that I might ask. So these are a group of problems that potentially could be on the exam or something like those. So looking at the types of things that we do with liquid chromatography, this is kind of a table that maybe gives us a little bit of guidance. So with LC or HPLC, and what is HPLC? So it's high, and then we can either call it pressure. Some people do. The P's for pressure. And some people say it's performance. And you'd think we'd figure that out by now, but we haven't. Liquid, and then chromatography. That's what HPLC stands for. All right, so basically it's what we're doing on a TLC plate, but now we're changing the particle size to smaller, and we're driving the flow with an external pump to have a constant flow rate. Where what we did with thin layer chromatography, using the capillary action pulls the mobile phase up the capillary plate until the point where the capillary action force meets the force of gravity and the solvent quits climbing. There's going to be some point where that wick action that's driving that will stop happening. And in HPLC, we have a pump that has a continuous flow, and it's going going all the time. Okay, so let's talk about the different types of chromatography of those types. So this kind of separates into a couple of different areas. So in the types of molecules you would use to separate. So it number one is looking at molar mass. So you've got small molecules up at the top, so smaller substances. And towards the bottom, you have things that are going to be the largest or larger. So you're looking at things that are molar mass of a 1,000 or greater. So that's protein complexes or large polysaccharides, strands of DNA, etc. And then another separation in this is that it looks at organic soluble versus water soluble. Okay, so are we looking at something that's where does it fall in the solubility? So in that, it starts to look at the ways that we could approach working those types of molecules. Okay, so let's talk about each one of those just a little bit and try to give some distinction to them. So things that are soluble in nonpolar solvents are typically things you might try to separate in absorption chromatography in normal phase, what we call normal phase. Things that are organic soluble in something like methanol may be something you would try to resolve in reverse phase. And sometimes you're going to have some small molecules that you could separate based on size, and those would be things maybe that would be soluble in something like THF. So with that, we could separate based on size using gel permeation chromatography. Um, and then if we go to the things that are water soluble, we have kind of two choices in water soluble things. We have things that are non-ionic versus things that are ionic. So non-ionic versus ionic. For non-ionic things, we usually separate those in reverse phase chromatography. For ionic, we separate those things in ion exchange or ion pair chromatography. And that was the technique that was used quite a bit at the bomb plant with the HPLCs that we saw up there. They were ion exchange chromatography, like the perchlorate ion that they were showing us that we're looking at. Now, once you start getting at larger molecules, typically larger molecules, you're not going to have partitioning or absorption. You're using a little bit different technique. So once you get over a couple of thousand mass, you kind of hit a little difference there. So I'm trying to get me choose a different color I haven't used. So let's choose this purple. So once you hit a couple of thousand, now you need to do things based on size. So you can do size basic separations, and if it's organic soluble, we call it gel permeation. If it's size-based separations and it's aqueous soluble, we call it gel filtration. Now, the mechanism of separation is the same. It's molecular entrapment, but we name it slightly differently. We also can separate large molecules either in ion exchange or with reverse phase. So for those polar substances that are water soluble, we can get a little bit of partitioning event on those as well. Okay, so that kind of gives you maybe a little bit of an idea of how you would apply some things into different techniques. And so I mentioned those different modes. So the partitioning, which we call reverse phase, absorption, which is called normal phase, ion exchange, size exclusion, and this minority one called affinity that I've added. And again, going back to the major difference between liquid chromatography, whether it's gravity flow or thin layer chromatography, and today's modern HPLC or UHPLC, which is probably another term, is simply particle size. Where gravity flow liquid chromatography uses large particles in the neighborhood of a tenth of a millimeter to 0.25 millimeters, which is 100 to 250 microns. That's low pressure to drop across the column. Where high performance liquid chromatography uses much, much smaller particles and requires a high pressure, and it requires a pump to get the solvent to go across the stationary phase. Now, the why do we want to use this? And this is probably the I would say the most important thing on this page. LC and HPLC gives us the ability to analyze non-volatile or thermally fragile or labile compounds directly. Now, why is that important? And the reason it's important is the next sentence. 75% of all the compounds in nature are non-volatiles. Okay? All the ions, all the cations, carbohydrates, amino acids, nucleic acids, you can't heat those types of things. Peptides, proteins, lipids, you can't heat those things up, and they go into a gas phase and run them across a gas chromatography column directly without some chemical derivatization or something else to them. And in some cases, things like proteins, you could never get into a gas phase. Well, shouldn't say you can get it in a gas phase with electrospray ionization or a MALDI source in mass spec, but they don't easily go to a gas phase. They're not going to run across a gas chromatograph. We'll say that. Okay, so while GC works great, it only covers about 20 to 25% of everything that's out there. So we need tools for the everything else, and that's where LC fills the gap, and that's the reason it's important. Uh, Big seller, so 5 billion a year in annual sales. In 2014 alone, and granted that's a dozen years ago, the Waters Corporation did 1.9 billion in sales with 6,200 employees. All right. So, why is there success in HPLC? Some key reasons is number one is that sensitivity greatly exceeds that of thin layer chromatography. The inline detectors allow easier quantification. It handles the things we can't see in GC, which are the non-volatiles and the thermally fragile compounds. And last, it's very easy to automate and reproduce. And there's a rule that we say in HPLC, and that is particle size rules. And the simple way to think about that is smaller is better. It's better in terms of efficiency, which is higher plate count, or number, however you want to say that. It is better in terms of, as a result, resolution. And that means simply separate more complex mixtures. Or separate a given mixture quicker. The downside to it is that, let's say the negative is increased pressure. So if you want to go small particle sizes, you pay for it with the equipment and the pressure they run at. So these bottom two figures are kind of telling of they share similar information, but they kind of show the changes that we've seen in chromatography stationary phases. So in the 1970s and 80s, we realized that going smaller was better. So 10 micron particles, 5 micron particles, and 3 micron particles. And kind of a standard particle size for HPLC has been 5 microns up until about, I'd say, 2005. And then after 2005, we started going, well, if you can get this small a curve with 5 microns and generate that much pressure, what happens if we go to smaller particles? And then we realized, well, let's just drop it down to 3. And when we drop it down to 3, now our Van Meter plot flattens out even more. And again, the smaller we are down here, the better. Secondly, we got this curve's almost going flat. So that means we can run at whatever flow rate, we can get away with the pressure in terms of the velocity, mils per minute or centimeters per second. And then we started going to, let's do more of these 3 micron particles in shorter columns so we can deal with the amount of pressure. Then there became a shift in about 2005 was, well, let's try to figure out how to deal with the pressure, and let's even go smaller. So that's what happened on the right-hand sides. So greater than 2005, we realize now we can go down to these even smaller than 3 micron particles, and it's even better. And now we can run at these extremely high flow rates where diffusion is not going to be much of a problem. We can deal with things. The small particle sizes allow mass transfer effects not to be as much as a problem. The downside to this is the pressure that's generated to go across a column. You're frequently in excess of 5,000 psi, and that requires some traditional HPLC typically runs at maybe 1,000 to 2,000 psi, pounds per square inch, and now we're in the 5,000 to 10,000 range. In fact, where we do a lot of chromatography, we use 1 micron particles, and our pressures are going to UHPLC, ultra high pressure liquid chromatography, ultra high performance liquid chromatography. We're running pressures of 15 to 25,000 psi, and there's a couple of companies that have kind of the market on the equipment to do that. But smaller is better. That's the simple way to think about it. So I taught a short course for Agilent chromatography, or for Agilent equipment, way back when it was called Hewlett Packard in the 1990s, when I was in graduate school at the National Cancer Institute, trying to let people understand about chromatography a little bit. But we talked about, they had some very good material that they developed that help visualize what's happening in these different modes of HPLC. So I stole in those from that presentation, and I think this is maybe one of the best ways that I like to see it. So in normal phase or absorption chromatography, you have your stationary phase here, and you're looking at physical absorption of your analyte to that. So you're looking at different types of molecular interactions between whatever the properties are of the stationary phase and that of some portion of the molecule. So whether it be polar interactions, where it be ion dipole interactions, it's some type of intermolecular force that's causing an attraction between the analyte molecule and the stationary phase, right? And that degree of that causes the retention. Now in reverse phase, the difference is, and let's go back to where we call normal phase. So normal phase, that needs to be defined. Normal phase uses a polar stationary phase and nonpolar solvents. And so the solvents really should use mobile phase. So a typical stationary phase is silicon dioxide. All right, so it's silicon dioxide surface, and then it's got SiOHs. So the surface of it's going to have the silicon ethers, like we talked about in GC, very polar surface. And things are going to stick to that based on how they have a dipole. Even if it's a temporary dipole, it can be introduced by the strong dipole on the silicon surface. You can also have an aluminum surface. There's a variety of different things you can use. Reverse phase chromatography switches that around. All right, so reverse phase, what happens is now you have the stationary phase that's over here, and it's frequently something like a silica particle, but what it has is a nonpolar liquid bound to the surface. And your station or your mobile phase is going to be a polar or a polar organic. All right. And as you increase the nonpolar content to that mobile phase, you're going to increase the strength of the solvent. So in reverse phase, the stationary phase is nonpolar, where the mobile phase is a polar organic. So that usually is going to be some mixture with water. So water plus maybe methanol, acetonitrile, acetonitrile, or isopropyl alcohol. There's a variety of different solvents that are water-soluble solvents that you can use. Okay, so this is where the partitioning comes from. You've got liquid phase 1, the mobile phase, and liquid phase 2, the stationary phase. This is where you have a partitioning event between those two. Now the next mode is the ion exchange. Ion exchange is where you have a fixed charge adhered to the stationary phase, and by opposites attract, it's an electrostatic interaction. So if you want to separate cations, you need to put an anion on your stationary phase to get those two things to attract each other, right? And then finally, the last mode of chromatography is size exclusion of the common four, and it works on the concept of a molecular entrapment. So what happens is your stationary has these pores in it, and these pores are where molecules that are big are blocked from entering, but small molecules can enter, diffuse in here, and then finally diffuse back out. But the bigger things, based on size, migrate down the column first. So the term that we used to call it molecular entrapment. So probably a better idea of what the stationary phase looks like is maybe little fingers like this. Now, not every pore is exactly the same size, but it's something to this degree. So bigger things can't get it in at all, so they're going to elute off very, very quick. Smaller things can get in maybe a little bit, so they're going to have an intermediate velocity. And things that are the absolute smallest molecules, they're going to get trapped in all these pores. They're going to move down the column the absolute slowest. Okay, so the retention order is that largest molecules elute first, smallest are last. And that's only predictable in size exclusion. The rest of them, it depends on the extent of the intermolecular forces. Okay, so HPLC uses packed columns that have stationary phase with dimensions that, again, are much smaller than those in GC. Right? So when I say that, the size of the particles. So typically, we want to try to use spherical particles, and we want them to be as uniform as possible, meaning monodispersed. We want them to all be the same size. I want them all to be exactly 3 microns, plus or minus 1/10 of a micron, as much as possible. And the why I want that is because I can pack uniform sizes tightly if they have similar dimensions. Now, if they vary in their dimensional sizes, what happens is you'll have big ones and small ones, but there won't be any space for the solvent to go through, and it yields up in tremendously high pressures. So we want uniform sizes in these. Okay, so the other thing that is different is that in LC columns, typically we design particles that have internal porosity. So what that means is that there is pores built into the stationary phase that allow the analyte to diffuse into. And this is kind of the big thing in the development of the technology, and that's shown on this slide. So these materials kind of look sponge-like, but they really have some enormous surface areas. So probably this is kind of a view of what we ideally we'd think a cross-section of a particle looks like. So it's not only the analyte can just interact at the surface, but the analyte can migrate down inside these things where there's stationary phase there too. All right, and that allows us to increase the surface area of these materials greatly, depending on how much this porosity is. So think of it as like a sponge would be the way to describe it. So there is bonded phase everywhere along these walls, and then the mobile phase is the stuff that's out in between in the center. So the mobile phase is going to be everywhere out in the open portion of the channel of these things. So a couple of images that I took were electron microscopes of different particles. So the one on the right is 50% porous, and its surface area, SA is surface area, is 150 square meters per gram. Okay, so you got to think about what that square meter means. So 150 square meters, that's 3 football field surface area per every 1 gram of material. And the particle that's on the left-hand side is even more porous. It's 70% porous. It has a surface area of 300 square meters per gram of material. So by having these very, very porous particles, what we can do is we can greatly increase the phase ratio by creating more stationary phase per mobile phase ratio, and we can use that to increase retention. And that is an adjustable parameter. Sometimes we use non-porous particles in reverse phase chromatography. Sometimes we use very porous particles. Okay, just talk minimally about the chemistry that's used to put these stationary phases on. That's certainly not a focus, but this would represent a silica particle, and you would react it with like a chlorosilane compound. This is a C18 tail. So what happens is it forms this silicon ether linkage, and it creates this 18 carbon tail. So that would be what we refer to as a C18 stationary phase. So it's C18 bound to this silica particle. All right, and it wouldn't be just that happening once. We would put literally tons and tons and tons on a surface so that it creates this non-polar layer. Right, and C18 is the most common type of stationary phase. Now, sometimes we use C4s and C8s and different things. There's a variety of different things that we do. But to try to increase stability, we can try to cross-link these things so that they bind to more than one SiOH group, silanol group. And then if there's any leftover silanol groups, I talked about this in the GC chapter, we do what's called end capping to try to eliminate those groups. We convert it into this trimethylsilane compound that's there. Okay, so we're trying to eliminate those SiOH groups from the surface. So there's a variety of different chemistries. We do different cross-linking. There's new types of particles that we're looking, especially at these small sizes. They're called what's called core shell particles. So what they have is they have a rigid core, so it can withstand high pressures, and then it has this spongy-like layer that is the porous material, and with that, they can withstand extremely high pressure. So if we look at pressure limits, so that in terms of that's around 20,000 psi can withstand, and they withstand good pH ranges. And these particles that are less than 3 microns, and they have a shell, a porous shell that's about a third of a micron thick, on top of a core that's about 1.9. So that's the particle one, and then they even go smaller. They have these particles that are sub 2 microns, so these 1.7 micron particles. And again, they're just going to higher and higher pressures, but with that is going to be higher and higher performance. So, and again, these are just new engineering that have been done on these particles to achieve better separations. All right, in the stationary phases, the most common ones that we have for reverse phase are the use of an octadecal, which is a C18, and it's commonly abbreviated ODS, which is just those 18 carbon tail. Or you have an octal, which is a C8, or you put a phenyl, which a phenyl group is just literally a phenyl group. So it's a benzene attached to that surface. Okay, those are the common ones that we use. And what happens is that when you look at the degree of intermolecular interactions that are going to occur, the larger the groups that have more nonpolar character associated with them are going to yield something that gives more retention. So if we look at things that are nonpolar molecules, they're going to be most retained with the C18, intermediate retained with the C8, and less retained with the phenyl. So we can start getting some order of separation with the different types of columns. And then if we look at the different types of things we could do to make the columns more polar, we can incorporate functional groups for nonpolar liquid chromatography that are things like amino groups, cyano groups, or diol groups. So we could add different types of intermolecular forces. So now we could look at maximizing, instead of London type forces, nonpolar forces, now we can go after polarity and look at polar forces. Lots of different choices, just like we had in GC. All right. If we look at the systems in HPLC, HPLC systems can be operated in isocratic mode, which means it's delivering a single mobile phase, or they can work in gradient mode where they're capable of changing the mobile phase composition during the course of the run as a function of time. So the way that these systems work is that they have some type of solvent reservoirs, and these are typically 1 liter size bottles. And then they're going to have some type of a mixing valve that says, okay, I'm pulling so much for this bottle and so much from this bottle, and up to, you can have a common system has 2 solvents, and then you can get a quaternary system that could pull from up to 4 solvents. It takes those things and it has a pump that creates that at a high pressure, and then it mixes it, and then it takes this fluid and it runs it through at a constant pressure, and it monitors the pressure for it, and it goes through an injection valve where we introduce the sample, and then it's carried onto the column, and it goes into the detector. And because this, again, is chromatography, it's a thermodynamic process, typically you're going to do this in a temp-controlled environment. All right, so even if it's ambient temperature, we want it to be a constant temperature in the system. So the pumping system is what really separates a quality HPLC from one that's not so good quality. So your low-end to high-end systems. So we want our pumps to generate up to 5,000 PSI, and this is traditional HPLC. Today in UHPLC, that number is substantially greater. So it's 25,000 PSI in UHPLC. Right, much higher pressures. It's a little bit different technologies. We want it to be pulse-free, so we want the pressure to be absolutely continuous. We want flow rates to be adjustable somewhere, and again, traditional HPLC, 1/10 of a mil up to maximum of 10 mils a minute. And we want to be able to reproduce the flow that we're doing at least at 0.5%. So the way that these work is something that looks like a syringe pump. So it has something that goes back and forth, and it's got seals on here. And as this pulls back, there are these what's called check valves. So they're ball check valves. So when this syringe is filling, this starts pulling back, this ball goes down and closes. So this is where your pressure side of the column, and that would be blocked at that point. But the solvent allows to come in, and it allows this syringe to pull. So imagine this cylinder coming back, I'll exaggerate the size, and it comes all the way back to here. Now when it starts going back this way, as the flow starts going out, this ball goes down and blocks this. This one goes up and allows the flow to go around, and now it's in pump mode. So a typical HPLC pump has 2 of these syringes, these pistons going back and forth. So one's filling and one's pumping. And then when the one that was pumping gets to the end and it has to refill, the other one starts pumping, and they're going back and forth. All right, so you have to have good seals in here that control that, and these things have to be cleaned. The seals wear out, these little ball valves wear out, so there's a lot of consumables in this, and it depends on how dirty your solvents are, what salts are in there that kind of grind up the plastic Teflon pieces. You can take care of these valves and they last for years, or you can be abusive to them and they last a matter of months. And consumables, I mean, these things, a seal kit may cost, to replace the seals on the pistons, assuming there's no other damage other than just the seals, maybe $500 for a seal kit. Check valves are usually at least a couple $100 a piece. Can be more when you go to the UHPLC system. Okay, then we go to the injector. We've got to create the pressure or introduce the sample into this pressurized loop. So I'm going to go back. So running up to here, we typically have anywhere from, just stick with traditional chromatography, from 2,000 to 3,000 PSI of flow. So whatever our flow rate is, Maybe a typical flow rate is 1 mil per minute of the solvent. That's coming in and going into the injector. So the injector is where we're going to introduce our sample. And the most common type of injector is a valve called the Rheodine valve. And this is what the Rheodine valve actually looks like. And the sample is going to be injected right here. So you're going to take your needle, and it's going to be a blunt needle. So it doesn't have to be sharp. It doesn't need to be a septum, but you're going to put it in there, and it's going to take the sample, and you're going to inject it into this loop. So depending on where this knob set that turns to the left or right, in the load position, the liquid would come in from the injector and come through and fill this fixed loop that's on the outside here. So that's what this guy is. All right. And that loop, depending on the diameter of the tubing and the length, it holds a fixed volume. So maybe it's 5 microliters, maybe it's 10 microliters, maybe it's 50, maybe it's 1. So, but it's a fixed volume in microliters. And if you flush any more through there, it's still just going to go out to waste and exit out. And then when you switch the valve to the load position, so the inject position, by twisting this valve so this thing turns, now what you've done is you've just changed the solvent coming in, which was normally going into the solvent in the load position. Now the solvent comes in, goes through the loop, it goes through the loop and then directly onto the column. So the loop just becomes part of the line. And now you can go through and you can rinse your syringe out and get it clean, get ready for the next time you're going to run, all right, in the load position. So the loop becomes part of the solvent stream is essentially what happens. And you can vary that loop by just unscrewing it, put a different size in there to change the injection volume. Now you can do a partial fill. So you could say, okay, if this is a 10 microliter loop, and I'll just put a number on there, you could try to inject just in portion of it. So you could say, okay, I'm only going to put 2 microliters in there. And you can do that okay. Robotics can do it really good, but it's harder for a person to do it by hand. So usually we work a fixed volume. Okay, what can we use for detectors? For detectors, anything imaginable. That's the short of what it comes to. Almost any type of analytical technique can be adopted to HPLC. So they can be based on bulk property detectors, or they can be very specific to the analyte. All right, so bulk property would be something equivalent to in GC, like the thermal conductivity. So we have a detector that works like that. I'll talk about that in a moment. More commonly, they're based on properties of the analyte. So let's cover some of those types of things. So the first one is absorbance. So absorbance chromatography in the UV vis. So usually the cell is a Z shape. So you got this thin stream of solvent coming through, and you run it through the cell that has a Z shape. Now the reason you're trying to do that is you want to keep the volume small, but Beer's law is dependent on path length. So we want to take and increase this path length up to a centimeter, 10 millimeters or a centimeter. They can either be based on filters on low-end instruments, but if we want tunability, we use a monochromator. If we want ultimate flexibility, like the ones they showed us at the bomb plant, we can base it with a diode array so we can get real-time spectra as components are eluting from our chromatogram. Okay, so here's an example, something like what they showed us at those plots at the plant in our tour last week, where you've got wavelength versus absorbance, and it's taken in this example a spectra every 5 seconds, and we can see these different cortisone-related compounds, these steroid-type compounds. Each one of them has a slightly different spectra in the UV vis, a different lambda max, and we could differentiate between which one of those compounds it was. Okay. And I'll tell you about today's standards. The spectra over 5 seconds is extremely slow. So most modern systems today will do 100 spectra per second in a high-speed system, and some will do 500. A few will do 1,000. But the thing you have to realize is the amount of data you're producing. So each one of these scans has got a certain inherent amount of data with it. So if you're doing those at all the wavelengths, and you're doing that 100 times a second, I mean, you can produce a single run that in chromatography that has a full gigabyte of data. So you start, I mean, a terabyte hard drive, which is a decent sized hard drive, you may fill that in a month or less. And so you have to figure out what data do you really want to keep. Right, we can do fluorescence. So in fluorescence, we can take in anything that has fluorescence properties. We can observe fluorescence at 90 degrees for excitation. Why? Much better sensitivity than absorbance. The problem with it is only a limited number of species fluoresce, but then we can do derivatization to add a fluorophore to the analyte, all right, and make it fluoresce, and then separate those things out. Now, the one that's more of a bulk property type detector that kind of the see everything is called refractive index. This is kind of equivalent to thermal conductivity in GC. What it does is look at the refraction of light as you have solutions that have a different refractive index than just the pure mobile phase. And it basically looks at how light's going through the sample compared to a reference sample, and how the light bends as it has a different refractive index than that of the reference solvent. And light's going to shift where more light or less light's going to be hitting the detector or sensor. It's pretty reliable. It's universal. The downside to it is it's pretty low sensitivity compared to the others. Now, when I say that, low sensitivity, you could easily determine something that is 0.1% versus 0.3%, but you couldn't use this detector to determine is it 1 part per million or 2 parts per million. Right. So a newer detector, new's not as new as it used to be, evaporative light scattering. So these detectors are about 20 years old. It's good for non-volatile species, and what it does is it creates particles from those non-volatile species, and it's a good option for things that don't have a chromophore. Again, it's a universal detection for non-volatiles, and it works on scattering of laser light. So much like the particle size detector that they use at the bomb plant to determine sizes of particles, it uses a technology something like that to look at how light is scattered. Not here to determine particle size for much, but is there particles or not? If we want to get to other types of technologies, electrochemical, and it can be based on electrical properties. So it could be conductivity for ion analysis. So that's what they were using at the bomb plant to detect like the perchlorate ion. So it conducts. The things in the background don't conduct. So you look at putting just simple conductivity as the detector. You could set it up so that you had a redox reaction. You could do amphiometry. So anything that could be oxidized or reduced, you could do that. And the kind of the technology that gives us the most information is mass spectrometry. And 25 years ago, mass spectrometry was still pretty hard to do, and that kind of changed 25, 30 years ago when it became commercialized, and it made it pretty household. So it is fairly expensive. So you're usually talking about $100,000 plus for just the mass spectrometer to do electrospray or atmospheric pressure chemical ionization. So just kind of give you an idea of some of the sensitivity comparisons for the different detectors. This is table 28.1 for HPLC. For absorbance, you can see typically in the picogram range. For fluorescence, you can drop that a 3 orders of magnitude, go to the femtogram range. Electrochemical, it's picogram. Refractive index, again, it's much, much higher concentration. It's nanogram, all right, 10 to the minus 9th. Conductivity is pretty good. Mass spectrometry is picogram or less, depending on if you're running scanning mode in mass spectrometry or you're running the SIMS mode. If you're running SIMS mode, you can get in that femtogram. If you use infrared, not near as sensitive, but you get some structural information. Again, the light scattering, photoionization is a newer one. It works pretty good, pretty decent sensitivity. You can have atomic emission, basically. So you could run it into a simple atomic emission source where you run it into a plasma and you look at the emission of all the elements there. You have a high enough temperature, it breaks everything down. So that gives you some elemental information. So if you want to know what has selenium in it or what has copper in it or something like that, you could see that. There's just a lot of different options that you have for detection. Okay, so the remainder of the chapter, so there's about almost 20 slides left, is going to be talking about how we optimize things a little bit. And I'm going to go through these a little quicker, especially after I get past these first couple. So I'd say this is one of the more important slides to understand something about retention. So if we compare reverse phase versus normal phase, I want you to be able to understand the order of retention that you have in reverse phase versus normal phase. And we have to go back to what the interactions are. So remember I told you that reverse phase uses a polar mobile phase, and normal phase or absorption uses a non-polar mobile phase. So if we look at the separation in normal phase chromatography that has a low polarity mobile phase, so what's going to happen is that compounds A, B, and C would separate, where C is the thing that is least retained. What happened to my pen here? All right, I have my pen locked up on me. All right, maybe I can get it back. Still not there. All right, maybe we're going to proceed here. Maybe we're not. I'm not 100%. So, okay. So, in this example, in A on the left-hand side, we're normal phase. So in normal phase, that means it's a polar stationary phase. And the things that are going to stick to it most are going to be the things that are most polar. So here are the polarities of the solute. Is A is the most polar, B is the intermediate, and then C is going to be the least polar. So that means that the thing that is least polar elutes first because it interacted with the stationary phase the least. And the thing that is most polar is going to be the thing that elutes last, right? Because it sticks to the stationary phase the most. So if I were to increase the polarity of the stationary phase, so go from something that was very nonpolar to something that was maybe intermediate polar, so going from like a solvent that was like a mobile phase that was hexane to something that was intermediate polarity like methylene chloride, which has a dipole moment, it's not a symmetric molecule, it increases the strength of the solvent and everything migrates a little quicker. So everything's migrating, the retention order doesn't change, everything migrates a little bit sooner. Okay, because this is a stronger solvent, stronger mobile phase, as I've increased the polarity of the solvent with increasing polarity of the mobile phase. Stationary phase stays the same. All right. So the retention order I expect is going from the least polar thing to the most polar thing. Now on the right-hand side is reverse phase chromatography. So imagine this as C18. So now I went to a non-polar stationary phase. I've reversed things, hence reverse phase. Now the order of retention is going to be the most polar thing is going to be the thing that comes off first. So A is the most polar. It's the first thing to elute off. It doesn't want to stick to that nonpolar stationary phase. And C is going to be the thing that is going to be least polar. Okay, it's the thing that wants to interact with the stationary phase the most. So this is a highly polar solvent. So maybe this is 90% water. 10% methanol solvent. And if I want to increase the strength of the solvent to get everything to elute off quicker, maybe I would change it to 50-50 water and the hydro or the organic, which would be methanol in this case. And that doesn't change the order, everything just comes off quicker. Okay, less retained. Now the big difference I want you to understand in these is that between the two techniques, the retention orders are reversed. In this one, it's B or C, B, A. In reverse phase, it's A, B, C. You're probably going to need to be able to predict that. Okay, so look at some of the example questions and the old exams or the problems in the back of the book and see if you can figure that out. Okay, so it's true or false, resolution decreases as the size of the particle decreases. So that is not true. So as the size of the particle decreases, so P decreases, that means you have an increase in the plate count, which means an increase in the resolution. So resolution goes up as particle size gets smaller. Okay, so composition of the mobile phase. Let's talk about that. In GC, the thing you control is the temperature. And that makes it pretty easy to control elution and the K prime. In LC, we do this by changing the composition of the mobile phase by changing the polarity of the solvent mixture. So what we do is we have to work a strategy to try to figure out what's the separation that I need. And that's what makes chromatography, liquid chromatography, even like thin layer chromatography, so challenging sometimes. What solvent do I need to use for thin layer chromatography to get the separation? And that's one of the things I was trying to demo in the lab that we did last semester, is that same stationary phase, 3 different solvents give you completely different types of separations. What do we really need? Okay, so it gives us some things we have to think about. What we need to think about is what with the interaction that we talked about in GC. What attracts what? And what are the attractions between the mobile phase and the stationary phase relative for that particular analyte? So in GC, we're only concerned really about 2 polarities, those of the analyte and there's the stationary phase. In LC, we have to add that of the mobile phase as well, because it's the one that we can control the easiest. When we're in GC, we've got a gas. It doesn't have a polarity associated with that. So when we choose our solvent, the rule of thumb that we use is we look at the polarity contributions from functional groups, and those, as we go to through this list, are things that are going to be the greatest polarity. So hydrocarbons are those smallest contributors, then ethers, and then esters, ketones, aldehydes, amides, amines, and finally alcohols are going to be the things that are going to be the most polar. So if we want to think about it in our polarity definition, it would be least polar on this side, most polar on this side. And hopefully that's trivial for you at this point in chemistry. So in reverse phase, what we're looking at is we're looking at stationary phases where we are looking at the opposite attraction to the polarity of the analytes. Okay, so we want to choose a mobile phase that has a different polarity associated than the stationary phase. So typically we use less polar bonded organic groups as the stationary phase. And we're going to do that. So the mobile phase is going to be the more polar thing that's there. So like the C18 versus a hydroorganic. And then the most common solvents that we use are mixtures of water and things like acetonitrile, which is a polar organic, or methanol, which is a polar organic. And we can control the mixture of the water versus the organic component to control the strength of that solvent. Now, you also can use, I mentioned these 2, you can also use THF, tetrahydrofuran, not as near as common, but it gives a little bit different selectivity. In normal phase, you have a lot different solvent selection. So in normal phase, the selection goes based on what's called the aerotropic series of solvents. And if we look at the eluent strength, this is that aerotropic series, values go from things like straight chain alkanes are typically a value of 0, something like N-hexane is the default value of 0. And then as we go to more and more polar compounds down the list of these organics, it's a stronger and stronger solvent. So something like diethyl ether has got a little bit more strength. Or if you went to something like dioxane, even more polarity, more strength. Methanol, even more. And you could go down the strength to greater and greater polar effects. So you can change the strength of the solvents. So this is that list called the aerotropic series. And again, as you go to a bigger number, you've got stronger at the bottom of this list. So stronger things towards the bottom in terms of solvent strength in normal phase chromatography. Now, the way that we deal with the general elution problem in liquid chromatography, HPLC, is that we perform a mobile phase gradient. We start with a weakly eluting solvent, and we get the things to separate that barely stick to the column to give them enough retention. And then over the course of the run, we increase the strength of the solvent or the mobile phase. So in this example of this separation of a mixture of pesticide components, it starts with 30% solvent, and it holds that for looks like 8 minutes, and then it ramps it up to looks like 45%, and then it holds that for whatever that is, 15 minutes, and then it more rapidly goes from 45 up to 80% in a faster gradient, and then holds that for a few minutes. And I would tell you that I'm the designer of this, and they've designed this run where it's happening within 40 minutes. They're getting all things off the column. Sure, I would say, yeah, that would be great, but there's just too much dead time in here. All right, that's resolution. It's great resolution, but you're wasting too much time. All this time you're pumping the mobile phase at 1 mil a minute. If it's hydroorganic, that's money. So I would try to compress this forward substantially by running a much sharper gradient. So if I'm going to design this and something in my lab, yeah, we're probably going to go like this initially, and then we're going to more rapidly go up to something like this, and probably end up with a shallower gradient at the end to pull these out. And I would at least cut the time of this separation in half, and it feel very comfortable I could do that. So there's too much wasted time in that separation. So I mean, it's a time is money thing, like we talked about. All right, so looking at the influence of the chain length in the stationary phase. So if this shows some example of some different compounds, and it's different chain lengths. So if our chain length is just a methyl, we get little retention. If we go up, so this would be a C1, and we go up to a C8, we start to get more retention of those compounds. So retention times are about double. The orders stay the same. If we go up to a C18, we've now got much greater retention. So it's pulling these things apart. Now, is it pulling them apart too much? That looks like pretty good resolution to me. The only thing I would want to do is try to bring that one in by changing a gradient in it. So we can change that characteristic of the stationary phase. And this is giving us some examples of some different solvent systems. And with a C18, so that's still a reverse phase separation. And it's isocratic. So these are all one solvent system. So here's an example of this mixture of these 6 steroid compounds. And this is acetonitrile water, so 41% acetonitrile. And 1, 2, and 3 are co-eluting. 4, 5, and 6 are just barely resolved, and 5 and 6 looks like it's co-eluting. All right, so now if we average K prime is 5, it's not sticking very much. So if we went to 70% water, so 30% acetonitrile, I'm sorry, weaker solvent, and now we've got separation of a couple other peaks. 5 and 6 come apart, but still I've got separate or co-elution of 1 and 3. And then if we went to use methanol instead of acetonitrile, that gives me a little bit of separation of 1 and 2. 3 is resolved. 4, 5, and 6 are good. And then in this case, if we switch to tetrahydrofuran, so 21% tetrahydrofuran, 1, 2, and 3 are resolved okay. 4, instead of being up here, switches down to the end, but it's co-eluting with 6 a little bit. And then kind of the combination that's kind of the best design in this, or best separation, is that acetonitrile is 11%, THF is 12%, 77% water for the balance, and now all 6 compounds are resolved in a 7-minute run. Now that probably took a long time to figure out, but you can figure it out. So here's an example of an amino acid analysis using reverse phase chromatography, and this was a separation developed by the Waters Corporation, and it took them a long time to figure out that they're going to do this complex gradient where it's a curve, not a linear gradient, where this is the curve gradient. This is the linear portion where they're changing the composition of the solvent, but they're separating these, we think, with, there's only 20 amino acids, we mean 30. Well, there's some non-standard amino acids in here that are amino acids in our body. It's just they're not common, and it's separating all of these, and this is over the course of a 47-minute run. So amino acid analysis, the time you do that separation and recover the column where you're ready to do another run, it takes typically an hour and 15 minutes. So just finish up talking about just some of the column sizes and dimensions. So give you an example of some of the different particle sizes and the different separations. So a 10 micron particle flowing at 1 mil a minute gives you a separation in about 9 minutes of these 4 compounds. If I take the particle size down to 3 microns, I can do the separation in about 1.2 minutes using a higher speed. Right? So I can do it much quicker. Quicker saves money. Looking at size of the column. So a standard size column that uses an ID of a 4.6 mil ID, right? So that's a standard size. So here's the 4.6 mil ID down at the bottom. The peaks they're wider, so they're not as tall. But if I go to a smaller ID down to these 1 micron IDs, so now I'm what's called a narrow bore or micro bore, my flow rates have slowed down substantially, and what I see is those peaks got a lot taller, right? So now they're easier to detect. So smaller IDs, better. So smaller column ID, certainly better. And this gives an example of another way it's better. The peaks are sharper. So this is conventional versus the micro bore. But the second thing is you're consuming flow rate at 1/10 amount. So 10% of the flow rate, so that means 10% of the solvents being consumed. You're not consuming as much as those hydroorganic solvents. So yes, I can see it. The peaks are sharper, they're taller, but it's also less solvent. All right, and I've talked about this one already. Just giving you some more examples of how solvent strength would change, and I've only got a few more slides here, so we're almost done. So this is varying the percent acetonitrile in water for these different solvent mixtures. So where B is the percent acetonitrile, and if we're at 90% acetonitrile, this would be the strongest of the solvents. Everything is co-eluting. Okay, so everything's coming off at once. At 70%, everything's still coming off at this 2.5 minute mark. So this is what we call the T naught, or the void time. Everything's co-eluting with the solvent front. If we drop it down to 50%, now here's the T naught peak, and we're starting to get some retention of these components. At 45%, a little bit more retention. You can see retention times out to 5 minutes. At 40%, better resolved. 35%, better resolved. And at 30%, these things are all well resolved, to the point where there's probably a little bit too much resolution in that. Okay, I'm wasting some time, but my runtime now is 35 plus minutes. Just going from 35% to 30% almost is 2 times the amount of time. So you got to figure out the balance. Where do we get what we want? All right, just talk about a couple of the other modes of chromatography right quick. With ion exchange chromatography, what we're doing is taking a stationary phase that has a charge to it, either cation or anionic resin. And then our mobile phase is going to be some water, and it's going to have some ion to it to compete with the ion of interest. Otherwise, the thing would never come off the column. And we can do something what's called ion pair chromatography, where we can take a nonpolar stationary phase like a C18, and we can bind to it something that has charge. So maybe this is a C10 group that has a quaternary amine at the end of it. So like an NH. So if that's a C10, it's a quaternary amine, so it's positively charged, so it would attract negatively charged analytes. Or you could put a sulfonate group on there if you wanted to attract cations. But using that, we can separate ionic compounds. So here's a mixture of anions we could separate. Or if we want to separate cations, we could put in anionic stationary phase and separate cations out. Size exclusion chromatography. So, and these are two different things. So size exclusion chromatography is where we're doing separations based on size. And again, we call those by name different. If it's aqueous based, we call it gel filtration. If it's organic based, it's gel permeation. Now, the key thing I want to say about size exclusion, only separates roughly on size. So you could separate something that is 500 AMUs from something that is, let's say, 900 or 800 AMUs. But you're not going to separate 500 versus 505. It won't give you that type of separation. Now, easily it can separate from something its size versus twice its size, but it can't give you very fine detail. Just another example of another amino acid analysis. So this is a even more complex mixture of amino acids, and this is a different technology than the one I showed you on the previous one. The good thing about this one is that it uses a linear gradient. So it's not linear. It's a pretty complex step too, but it's not the curved gradient that the water is going to use, and it separates all these amino acids out. We can separate carbohydrates out by separating mixtures of carbohydrates. This is a refractive index detector. So you use a polar stationary phase to attract the polar carbohydrates. And the solvent you're using, water. Okay, pretty simple. The polyaromatic hydrocarbons, we can separate those. Here we're using a column that is a proprietary column, so it's a mixture of C8 and it has some polar or some benzene groups in it as well. So it attracts these aromatic, has pi-pi interactions, and you're using a high organic content, higher than normal for reverse phase. You're going from 50% up to about 100% organic, or acetonitrile is the solvent, but it lets you separate. This is what they call the K8 or 16 mixtures of polyaromatic hydrocarbons. These are things we're concerned about being carcinogens, and we don't want to have these in the environment. We definitely don't want to consume these, so we study these to make sure that they're not in our drinking water. And just want to finish up on this one slide to kind of show you where the evolution has changed to. So this is a technique called top-down proteomics. And top-down proteomics is where you take a protein and you digest that protein with an enzyme like trypsin, which cuts its specific amino acid, and it breaks it into pieces. So it slices it up into these peptide fragments. And then you can take not only just from a single protein, but you can take a whole cell or tissue sample and lyse it all and analyze them all simultaneously and analyze it all in a single run. And when you run it into the highest resolution liquid chromatography, so you do the LCMS on it. So this is the LC, this is UHPLC, ultra high performance liquid chromatography. So this is using the sub 1 micron particles, and they do this separation slowly. So this is a 10-hour run, but there are all these peaks that are eluting as a function of time, literally 100,000 peaks that are in here. Okay, from 100,000 different peptides that you're eluting out with this, and you detect them with high resolution mass spec for quantification. And then each one of those you do mass spec on. So you take that and you do fragmentation of that selected peptide, and you can work through the peptide sequence. That allows us to detect everything at once. And this is kind of where we stand today with the technology and how much it has changed. So you can take in a high-end separation using something like an Orbitrap high-resolution mass spectrometer. You can quantify 10,000 different proteins in a single run, right? And using the technology that exists. And that was unheard of 20 years ago. Now, something I want you to think about, just the data set on this would be terabytes of data from the mass spectrometer, and then it's going to take an extremely long period of time to sort through that data. Okay, so even using AI with the aid today, you may collect this run over 6 hours. It may spend you 6 months to sort through all the data that you have. That's how the technology has changed. Okay, so that's instrumental analysis. So that's all we've got, and hope you get a chance to view this, and we can talk about it a little bit in class if needed.